Okay, so let's begin today's class. So, welcome again to FAST being brought to you from IIT Madras and IIT Tirupati. So, we are in the final lecture of this week and we are closing on this module dedicated to femtosecond laser pulses. As always, these are the 4 books we are depending upon as primary references and sources of information, and thanks to Professor Trebino for his materials and inputs which he generously shares with us. So, let us continue to recap the previous week's lectures and previous sections of study, and today advance our current agenda, where we have essentially dedicated time and effort this week largely to study about chirp. So, once again today we will recap the salient features from the start of the section on the formal description of pulses, and we can further we will further our current week's agenda to explore the chirp and the interpretation of the phase terms in the spectral domain description of pulses. And in today's lecture, we will go into the next two advancements, which are on the propagation of pulses or how to treat that, as well as the time bandwidth product. So, again for the quick recap, the iconic pulse that we want to keep in mind is no longer an unchirped pulse, whereas here it is chirped. It has a nearly Gaussian envelope, and in this case the chirp is positive. So, the frequency increases from in the increasing direction of time, which is left to right in this plot. The complete description of the pulse which is of interest to us here is essentially captured in this equation, where on the left hand side we have the real electric field, and which is described completely in terms of an amplitude function, a real amplitude function, which is the square root of I of t, where I is the intensity function, as well as the corresponding phase, which is phi of t, which is in the argument of the complex exponent. Both of these are relatively slow variations in time as compared to the carrier frequency, which which has an angular frequency value of omega naught, which is set for a given condition where we describe the pulse. Now, we Fourier transform this, and in the frequency domain we have two pieces owing to the way in which we describe the real electric field in the time domain. This gives us two pieces, one on the positive frequency side and the other on the negative frequency side, both of which contain a spectral amplitude which corresponds to the amplitude that we saw in the time domain. The spectrum is the spectral intensity, it is the analog of the temporal intensity or intensity in the time domain, and the square root of the function s essentially governs the spectral envelope or spectral amplitude of this frequency domain description of this pulse. Likewise, in the argument to the complex exponential function, we have the spectral phase function phi of omega. These two functions contain complete information about the pulse, whereas we also have, owing to our prescription for the pulse in the time domain, a second term which is in the negative frequency side, and this does not contain any additional information as compared to the positive frequency side of things. The phi in the time domain, the phase function, is essentially to be looked at as a Taylor series which describes the function in its entirety, albeit this would be an infinite series, but we are often concerned about the leading order terms, the first order being the term that is related to the instantaneous frequency, and for well behaved pulses it is usually the first few terms that matter. We saw that. A corresponding description in the frequency domain would involve once again expanding the spectral phase function phi of omega this time, in the frequency domain, which wherein the Taylor expansion about omega naught leads us to a phi naught plus phi 1 omega minus omega naught phi 2 omega minus omega naught the whole squared divided by 2 factorial and so on and so forth. Now, here phi 1 has the interpretation of the group delay, which we have seen quite a lot, and followed by the dispersion of group delay or group delay dispersion. The zeroth order phase is important in the case of very few cycle pulses, a single or maybe just a little longer, where the shape of the electric field gets very characteristically defined by the value that the zeroth order phase has. So, this one could call this the CE phase or the carrier envelope phase, whereas for longer pulses, even with a pulse that is longer than this yet very short in some sort of absolute standard, where we have just 4 cycles within the full width at half maximum, there this value of that phi naught takes does not seem to matter too much. So, we looked at then the phenomenon of linear chirp or chirp, which arises out of second order phase terms, the second order term in the spectral phase. So, the impact of the linearly chirped Gaussian pulse is something we explored in the previous lecture, where once again the impact of the chirp in the case of Gaussian pulses, we explored that in the time domain by considering a pulse of the following type, where we had E naught exponent t by t g the whole square with a negative sign prefixing that, which becomes the amplitude function of the Gaussian pulse, it is the real amplitude, followed by then the carrier wave and the chirp term, which is now essentially a term depending on t square. Now, we call this chirp linear because the instantaneous frequency can be obtained by differentiating the argument to this complex exponential function, in which case we would obtain omega naught plus 2 beta, or if it was negative, if beta is definitely negative, then it is omega naught minus 2 absolute value of beta times t. So, in either case the instantaneous frequency is what defines the order of the chirp. If it is then if the instantaneous frequency depends linearly in time, then it is the pulse is said to be linearly chirped. If it has a quadratic dependence, then it would be called a quadratic chirp and so on. So, of course, once again just a reminder of a reminder that we are expanding the spectral phase function in terms of omega in the Taylor series, and we have concerned ourselves so far with group delay phi 1 and group delay dispersion phi 2, right. So, for so called well behaved pulses, we would only need leading order terms in the Taylor series. So, we considered also an example of Fourier transforming a chirp pulse, where the amplitude function is minus alpha t square, where alpha is proportional to the square root of alpha is inversely proportional to a measure of the width of the pulse. We Fourier transformed this and we obtained an expression for the amplitude or the spectral amplitude and the spectral phases of this pulse, and we deduce the group delay for this Gaussian pulse and so on and so forth, right. But we then looked at instructive examples of positively linearly chirped pulse, a pulse carrying a positive linear chirp, how it looks in the frequency domain. The instantaneous frequency is essentially varying linearly in time, whereas the instantaneous phase factor is essentially parabolic in both frequency and time. In the case of frequency, it is an upward opening parabola, in the case of time it is a downward opening parabola, and we can transform from wave frequency to wavelength coordinates. Okay, so far we set things up nicely, and we jumped or we delved into the third order phase term in our earlier discussion. Okay, before we proceed, I kind of promised you or rather brought up the issue of the the phenomenon of chirp playing a role in the case of gravitational wave signals, and this is the sort of a copy of the data that was uncovered by the first LIGO signal, the first gravitational wave signal measured by mankind at the two LIGO observatories, Hanford and Livingston, and in both cases you can see that the frequency of the observed signal, which look at the values here, it is in some hundreds of hertz, you can say tens to hundreds of hertz. So, you can see that this natural signal, which of course is not a very pretty sinusoidal wave, but it does have a bit of some noisy features, which is the instrument also having I mean bringing out noise and whatever not. But then it is evident that the frequency of the chirp is the frequency of this gravitational wave signal, which is a pulse signal, is increasing, as you see from the early cycles 1, 2, 3, 4, you can see this the frequency has increased and it maximizes at some point a little before between 0.9 and 1 seconds, and that the frequency itself is actually plotted in a color plot, where white signifies highest value and the color going towards black is lower values. Here you can see that essentially as a function of time, the frequency is changing somewhat quadratically. So, it does carry even a nonlinear chirp, it seems. Of course, this signal was produced by the merger of two black holes. This is some sort of an, you can say, artist's impression of two black holes merging. In fact, I was able to even find for that matter a little acoustic representation on YouTube. I hope, okay, I should not talk at the moment then. So, apparently that is how the merger of two black holes is supposed to sound if it was an essentially a strong enough acoustic wave, because I am not entirely sure we can hear these low frequencies, but some amount of acoustic graphics that gives us an idea of what is happening. So, chirp is everywhere, it is very natural to signals, linear chirp at least, linear, and but you see in this case that we have considered here, it is a bit of an extraordinary case of the linear chirp or the quadratic phase term being 0, whereas the cubic phase term and the cubic or in this case the cubic phase term in the time domain is non-zero. It is a little bit artificial. So, we can think of this as a sort of distortion or perturbation riding on top of the linear phase or the second order phase term, right. So, as I told you in the previous lecture, so we could have a quadratic chirp or a nonlinear chirp, as in this case omega naught plus a factor times t square being the instantaneous frequency, arising out of nonlinearities. We had quite some detailed discussion, or I tried to give you an impromptu impression of how a nonlinear process, for example, can impact this. The other aspect is also that dispersion also for a sufficiently broad bandwidth of a pulse can introduce nonlinear chirping over sufficient lengths of propagation in media and so on. So, we examine once again the consequence of the third order phase spectral phase term or the quadratic chirp in the in the time domain, right. So, in the frequency domain, the amplitude of the pulse remains Gaussian. There is not much to argue about that. The Group delay is of course quadratic. Okay, this is wavelength scale. So, the all the parabolic behavior is skewed, whereas here the amplitude of the pulse, if you see as we did yesterday, it shows the pulse breaking into satellite pulses. The main pulse in the first part, the main pulse, and then satellite pulses too, right. So, that's a sort of view we develop for this kind of a pulse with little ringing like features that follow the leading main feature in time. If the quadratic chirp had negative sign, that is gamma had a negative sign instead of being positive, as we have chosen by default for no particular reason. If this pulse was negatively quadratically chirped, then we would have the pulselets, the satellites leading the main pulse, both of which can happen. Okay. But then you can see that in these cases the spectrum, right, it essentially can have a certain behavior in time which is not necessarily uh, linear in terms of its instantaneous frequency. So, so much for the quadratic chirp. The quadratic chirp factor phi 3, which we have here, uh, phi 3 has units of second cube or femtosecond cube, or as the case may be, it could be radian femtosecond cube, the manner in which we choose to describe it. As I brought this up yesterday again, see if we peg to the cyclical frequency as the variable of interest nu instead of omega, the radial frequency, the units of cyclical frequency are femtosecond inverse. Then time gets defined as femtosecond in femtoseconds, whereas the phase, the total phase, spectral phase is still measured in radians, right. So, this is still measured in radians, and the spectral phase has this term which goes like phi 3 divided by 3 factorial in the way we have defined it, multiplying the frequency that we have chosen to use frequencies. We have chosen 1 over femtosecond unit. So, this must be nu by nu naught. So, okay. So, this side also the argument should be nu, in which case now phi 3 evidently has units of femtosecond cube to nullify the femtosecond inverse cube from the nus, but then it must give us radians for the left hand side. So, that is why the units are so. Okay. So, that is as much about third order spectral phase of quadratically chirped. So, two key take home messages: it splits the pulse into having satellite pulses, and you also have, as a consequence of this, lagging or leading satellite pulses based on the sign of gamma, and the units of the phi 3 coefficient, depending on how you are going to present it, is either femtosecond cube, or in this case in a more accurate way it is radians times femtosecond cube. Okay. So, let us now proceed to fourth order spectral phase. So, fourth order spectral phase would essentially have the following. We consider a fourth order spectral phase and look at the coefficient that we are considering here. It is 5000 inverse femtoseconds in this example, and it is plotted out over here. All right. The fourth order spectral phase has the consequence above all to create these sort of pedestals in the time domain. You see there is a main pulse, you can say a wing, a symmetric wing on either side is sort of created by the owing to the fourth order spectral phase. Maybe I can highlight the regions for the wings, right, and the rest of the pulse remains easily close to a Gaussian. So, the main point being here that what we are considering is again the envelope of the pulse in the spectral domain or the spectrum still remains a Gaussian, whereas what we see is in the frequency domain we are only considering a spectral phase which is quadratic. Once again I must emphasize the fact that this implies that the first 3 coefficients up to or first 4 coefficients from phi 0 to phi 3 have been artificially set to 0, in which case we have this purely quartic behavior of the phase function, okay, and that leads to an instantaneous frequency, okay, which is cubic. See the cubic nature of the instantaneous frequency across t is equal to 0, which is the maximum of the which is aligned here to the maximum of the Gaussian envelope. Okay, so that is the cubic sort of behavior, and I mean we know what happens in the wavelength domain. It skews things up a bit, but then you can look then at this is the instantaneous frequency. The instantaneous temporal phase also in this case has a kind of quartic behavior. Okay. So, we can do some sort of visual analysis if you wish of why the wings are formed, you can easily or we can figure this out. Okay. If we now look at this region where the amplitude of the Gaussian is predominant, okay, you can say this is more than 50% of the max, right. In this region from where from the constituent frequencies you can say make the largest contribution, okay, to forming this time domain feature of the pulse. This time domain feature is simply a weighted sum of the amplitude times the phase factor of all these frequencies, values roughly between a little less than 0.35 to 0.4 femtosecond inverse. So, in this region the amplitude function being Gaussian, there is maximum contribution, weighted contribution to your actual to the pulse in the time domain. These are summing up to form this pulse. The interesting thing to note here is that if you follow the spectral phase here, owing to the quartic nature, there are no cubic and quadratic terms in the spectral phase. There is just the quartic term. So, this pulse again is not a realistic scenario we are considering for the pulse. Only the higher fourth order term in a perturbative expansion is non-zero, the rest are 0. It is a little strange. I do not even have an idea how this can be realized in a lab. But here the spectral phase is fairly flat, whether the phase value is 0 or here it has a value of something like plus minus, I mean a plus 10 radian, but nearly constant. That does not really matter for the moment, but what matters is the shape of the this local shape of the spectral phase function. If for whatever reason in this dominant region, if I see what happens to, if I inverse Fourier transform this piece, I would get a nice Gaussian structure centered about time t is equal to 0 here, with a carrier frequency which corresponds to about 0.375 femtosecond inverse, right. So, it is no, and the rest is a linear sum of the remaining, sorry, and the rest is a linear sum of the remaining regions of the real tails, where of course, the phase factor has shown up its head, and it starts to rapidly increase with increasing magnitude of the constituent frequencies. So, they make a smaller contribution. Okay. So, they make a smaller contribution at of two kinds. They make a smaller contribution with, there is still, if you carefully watch this plot, you can see that on the left side here, the instantaneous frequency is lower than on the lagging tail, you see. So, that contribution comes from the 0.3 femtosecond inverse region, and this contribution is predominantly coming from the 0.45 femtosecond inverse region of the spectrum, adding up to give these features. In other words, basically these form these are responsible, you can blame the wings of the pulse, which if not desirable, then it can be blamed on the fact that the pulse has such a large bandwidth, and for some reason the phase function here is not linear, which is really the case. It is easier to distort a broader band pulse and make that collect a quadratic chirp as compared to a pulse which is broader in time and has a narrower spectrum, right, just by things like mere propagation. Anyway, so that is I mean, that is sort of interpretation that we can think of why these wings are formed. Of course, the other way is to take a computer and just take these phase and amplitude profiles and just brute force do a fast Fourier transform. It will result in similar results, but the insight one gains from this is merely arising out of the fact that in the case of the quartic spectral phase dependence on frequency, there is a flat region, a nearly flat region like a bucket, or we can call this like a bathtub shape for the spectral phase, which is responsible for this. You can say, you can view this as a Gaussian pulse with a quartic distortion, I mean a wing which is a distortion owing to the quartic phase. Okay, so that is what I meant by saying we can view these terms as terms that distort the ideal pulse. So, quite similar, it is in the case of the negative value for phi 0. In the case of the negative value, this effect is quite symmetric. So, on either side we have the wings, but you see the higher frequencies are on the leading edge, wing on the leading edge, and the lower frequency instantaneous frequencies are on the lagging wing of the pulse, okay, as one should again expect. Now, we are going to look at the consequence of the fifth order spectral phase term alone. Okay. What do we expect there? So, my guess before I flip this slide is it is going to be somewhat similar to the third order term. There will be some splitting sort of effect. Okay. So, in some sense the odd orders sort of tend to have this effect, and indeed it does. Of course, one can argue that I had some I cheated by already knowing what was in the view graph. That is a fair enough accusation if you wish, but the fact remains that here again look at the quartic phase, it is quite flat, okay, which is the reason why a major part of the time domain in the time domain, a major part of the Gaussian pulse seems to be preserved, and then it seems to have broken off into tiny satellites on one side of the pulse. So, a seventh order spectral phase would also have like a similar effect. The number of appreciable satellite pulses would increase. The pulse would be split even more in the case of the seventh order spectral phase term, or if I consider a pulse with just the seventh order spectral phase, when compared to the original Gaussian pulse, where this term would have been turned off to 0. Okay. So, in that sense, these are to be viewed as perturbations or distortions to the leading Gaussian pulses, which could carry a linear chirp and so on. So, identically for phi 5 of minus 44,000 radians, again note radians times femtosecond to the power 5, you have satellites on the sort of leading edge. Okay.